Previously, we have introduced the equivalence relation. In this section, we will discuss the equivalence classes and some of their essential properties. First, let us look at the definition. Let X be an element of the set A equipped with an equivalence relation tilde. We will consider a subset of A consisting of all elements to which X is related, and call it the equivalence class represented by X. We will put a pair of squared brackets around X to represent this class. Be careful. Although X is an element of A, the equivalence class represented by X is a subset of A. To get some feelings, let us recall some of the equivalence relations we have defined on the set of real numbers. For each of them, we will identify what is the equivalence class represented by the number 1. In our first example, X is related to Y if and only if X is equal to Y. Thus, 1 is only related to 1 itself. In other words, the equivalence class represented by 1 in this case is a singleton set consisting of 1 itself. In our second example, X is related to Y if and only if the absolute value of X is equal to the absolute value of Y. Now, the only real numbers with absolute value equal to 1 are precisely 1 and -1. In other words, in this case, the equivalence class represented by 1 consists of two elements, namely 1 and -1. In our third example, X is related to Y if and only if either the product of X, Y is positive or they are both equal to 0. Now, given an arbitrary real number Y, since 1 itself is not equal to 0, 1 is related to Y if and only if Y itself is positive. As a result, the equivalence class represented by 1 in this case is precisely the set of positive real numbers. Finally, let us consider the universal relation, in which case any two real numbers are related to each other. In particular, 1 is related to any real number. As a consequence, the equivalence class represented by 1 in this case is the entire set of real numbers. You see that although all these equivalence relations are imposed on the same set, that is, the set of real numbers, however, since they are different relations, even for the same element, its equivalence class may differ depending on which equivalence relation we are considering. Now, assume that we have a set A equipped with an equivalence relation. Let us pick two elements, X and Y. Now we can consider the equivalence class represented by X as well as that represented by Y. The question is, what can we say for these as subsets of A? In the rest of this section, we provide the answer to this question based on the following two propositions. Let us start from the first proposition. Let A be a non-empty set equipped with an equivalence relation. Then, for arbitrary elements X and Y, X is related to Y if and only if the equivalence class of X is equal to the equivalence class of Y. Recall that each equivalence class is a subset of A. Thus, the equality here is a set equality, meaning that these two as subsets of A are identical. We will first prove the only if part. To this end, let us assume that X is related to Y. Let Z be an arbitrary element in the equivalence class of Y. That is, Y is related to Z. Now that X is related to Y and Y is related to Z, by transitivity, we see that X is related to Z. That is, Z is in the equivalence class represented by X as well. At this moment, we have shown that the equivalence class represented by Y is a subset of the equivalence class represented by X. Furthermore, since X is related to Y, by symmetry, Y is also related to X. We can thus argue in a similar way and conclude that the equivalence class represented by X is also a subset of the equivalence class represented by Y. Now, this double set inclusion indicates that these two equivalence classes are identical sets. Next, let us proceed with the if part. Assume that the equivalence class of X is equal to the equivalence class of Y. Now, by reflexivity, we know that Y belongs to the equivalence class of itself. But now, under our assumption, we see that Y is in the equivalence class of X. And by definition, This means x is related to y. This finishes the proof of this proposition. Next, let us look at the second proposition, which claims the following. Let A be a non-empty set equipped with an equivalence relation. Then for any elements x and y in A, x is not related to y if and only if the equivalence class of x and the equivalence class of y are disjoint, meaning that their intersection is empty. As before, let us first work on the only if part by assuming that x is not related to y. Now, suppose to the contrary that the equivalence class of x and the equivalence class of y have some common elements, namely z. That is, x is related to z and y is related to z. Now, since y is related to z, by symmetry, z is related to y. But since x is related to z, now the transitivity implies that x is related to y. We have thus reached a contradiction. As a result, the equivalence class of x and the equivalence class of y must be disjoint. Next, let us work on the if part by assuming that these two equivalence classes are disjoint. Again, let us use the proof by contradiction by assuming to the contrary that x is related to y. Now, by the definition, y is in the equivalence class of x. Moreover, thanks to the reflexivity, y is also in the equivalence class of y. In other words, y is a common element of these two equivalence classes, contradicting that they are disjoint. As a consequence, x is not related to y. This finishes the proof for this proposition. In the next section, we will illustrate how these two propositions can help us achieve an important result on classification when the set is equipped with an equivalence relation. That is, the partition by equivalence classes.